Simpson Create Integration Rule is a numerical approach for estimating the value of a definite integral. This rule is an improvement on the basic Simpson's 1-3 integration rule. And there is a difference between 1-3 integration rule and 3-8 integration rule. Basically, 1-3 integration rules utilize quadratic interpolation, whereas Simpson's 3-8 rule uses cubic interpolation, resulting in a more accurate approximation of the case. We use Simpson's 3-8 integration rule for both C++ and MATLAB. For implementation C++, the first step we need to do is we need to define the function of fx, which is the functions that we need to integrate. The second step is write a function that takes the lower limit a, upper limit b, and the number of intervals n. The third step is we need to return the approximate integral using Simpson's rule that prompt the user to input the necessary value. We need to find the output of the result. And for implementation MATLAB, the first step is the same with C++, which is the first one is we need to define the function fx. But this function fx is an anonymous function.
The methodology of implementing Simpson's 3/8 rule is highlighted into three, which is the first one is divide the interval of integration AB into a number of subintervals, which is n, which number that multiply by 3 equal with width h. So the equation of width is h equal to b minus a over n. Secondly, evaluate the function at the endpoints a and b and at n minus 1, equally spaced interior points. Define these functions values as fa, fb, fx1, fx2 until fxn minus 1. And finally, use the formula to compute the approximate integral.
Here is a pseudocode for an implementation of Simpson's integration rule in C++, where Simpson's rule is basically a numerical integration method that approximates the definite integral of a function. It is more accurate than the trapezoidal rule, but less accurate than Gaussian quadrature. And the function that is going to be integrated in the pseudocode is basically fx equals to square root of 1 minus x squared. And this is the standard trigonometric function for the sine of an angle, but then with the argument squared. Which means that the function represents the distance from the origin to the point on the unit circle as the angle varies from 0 to pi over 2. The main function of the code is going to be Simpson's rule function. And it takes three parameters, which includes the lower limit a, the upper limit b, and the number of intervals n. It then calculates the integral of the function fx from a to b using Simpson's rule. The function calculates the width of each interval h by dividing the difference between the upper and the lower limits, which is b minus a, by the number of intervals n. Then it will calculate the value of the function at the lower limit and the upper limit b and adds this to the sum. So the function then will iterate over each interval between the lower limit and the upper limit, and if the current interval index I is even, it will add twice the value of the function at the midpoint of the current interval, which is a plus I times beta h, to the sum. And if the current interval index is odd, it adds 4 times the value of the function at the midpoint of the current interval, which is a plus I times h to the sum. And after calculating the sum for all intervals, the function then multiplies the width of each interval h over 3 by the sum and will return this as the result of the integration. And the main function of the code prompts the user to enter the lower limit, the upper limit, and number of intervals. Then it will call the Simpson's rule function with these parameters. Then it will print the result of the integration. In order to use this code, it needs to use a compiler in C++, and then compile them and run the compile program, and then the program will prompt you to enter the lower limit, upper limit, and number of intervals. And after these values are entered, the program will then calculate the integral of the function fx from the lower limit a to the upper limit b using Simpson's rule and print the result to the user. Here's how the terminal output of the coding would look like. So first thing first that is going to appear on the screen as we run the code is basically enter the lower limit, where we will have to enter the number that we want, which in our case we did 0. And then after we enter the number of the lower limit, it will then appear the second line, which is enter the upper limit, which we did 1. And then after that, it will also ask you to enter the number of intervals, where it depends on you, and in our case we did 24. And it shows, at the end of the day, it shows the result of the calculation from the coding, which is, it says integration result using Simpson's rule is 0.78442.
For flowchart C++, there is a starting point, and we enter the limit a, b, n, and then we sum using the fa plus fb until we processing we get the result, which is we print integration result using Simpson's rule.
Next, this is the coding for MATLAB software. For the first part of the coding, we need the function, and we insert the function of square root 1 minus x squared, and then we need the user to insert the value of a, b, and n. From this input by the user, we compute the value of h using the equation, and then to check the value of n, that which is the n must be multiplied by 3, we use the if function, where the n is divided by 3. If the remainder is not equal to 0, the program will print out n must be the number that multiplied by 3. So for the next part, we're gonna compute the equation of integration. So from the long equation, we have 3 in bracket y1 plus y2, but there's a missing of y3. So we use the si equal to empty bracket. So whenever the number of y of s and the I condition is overlap, it will be terminated. So since I is in the multiple of 3, so the y that multiple by 3 will be terminated. And then we have 2 in bracket y3 plus y6. So there's the value that multiply by 3. So we use the condition I equal to 3 ratio 3 ratio n minus 1. So this is all we're gonna be sum up as s3 equal to sum of si, and then so equal to sum of s, which is the 3 in bracket y1 plus y2 plus y4 until n minus 1. And then all of this equation will be arranged in the result, which is out equal to 3 times h over 8 multiplied by fa plus fb plus 3 multiplied by so, and plus with 2 multiplied by s3, and then the program will print out the value of integration. Using the same value of a, b, and n with the C++ coding, the result will be printed out at the command window.
The figure shown is the flowchart of the MATLAB, which consists of start and then input and then the h formula and then the condition, which is rem and 3 equal to 0. And if condition is true, it appears print n must be the number that multiplied by 3, whereas if the condition is false, it appears print the value of integration out. And lastly, end. All in all, both C++ and MATLAB can implement the Simpson's 3/8 integration rule with comparable precision. However, MATLAB shows the result with more precision. This is proven by the output that was obtained using the C++ is 0.78442 compared to the output that we obtained from MATLAB, which is 0.784207. So the comparison between C++ and MATLAB implementations underscores the flexibility of the algorithm across different computational environments. Through this exploration, it becomes evident that Simpson's 3/8 rule is a robust method for numerical integration, offering a balance between simplicity and accuracy. Users in engineering fields can benefit from the presented code samples and discussions to employ this integration rule effectively in their computational tasks, enhancing their ability to approximate definite integrals with confidence and precision.